Hi everyone, welcome to our third video in our series on graph theory. This video serves as an introduction to Hamiltonian circuits. So here we go. Tomorrow when you leave class, suppose that you need to stop at all of the places on the map below. What route will you take and why? Okay, so we're going to start right here on campus, and we're going to assume, by the way, that we live on campus, so we've got to return there when we're done. We've got to visit all of these places. Which route are you going to take and why? So maybe you want to get the farther away places out of the way first. So you'll kind of start by going to Jewel, to the grocery store to pick up a couple of things, swing by Target, back down to the restaurant, and then kind of work your way back closer to home, by the cleaners, to the bank, and then back to campus where you started. So that's a possible route that you could take to visit all of these locations and end up back where you started. But maybe you think, it's not a great idea to go to the grocery store first. Maybe you think that doesn't make a ton of sense. So instead, when you leave campus, maybe you're going to first go to the cleaners to pick something up. You want to get there before they close, and to the bank to get a little bit of cash on hand. Then you're going to go to the restaurant because you've got to meet some friends to eat, and because you want to go to the restaurant before you do your grocery shopping so you're not so hungry. You'll leave the restaurant and swing by Target for a couple things, then to Jewel to pick up maybe a prescription or a couple little groceries, and then because you've got the ice cream in your car, you're going to do that last, and then you're going to head back home to North Central. Okay, so those are just a couple of the routes you could take. You may think of a completely different option that would work as well. But the goal, right, is to visit all of these locations and then end up back where we started. And so in terms of this particular graph, we think of this as visiting all of the vertices of the graph. And that's what we're going to be talking about in this video, our Hamiltonian circuits. First, a quick review. In the past, we've talked about Euler circuits. So an Euler circuit, you may recall, is a circuit that covers each edge of a graph once, but not more than once. So here's an example of a graph with an Euler circuit. So we started in the top left-hand corner. We want to visit every edge exactly once in our Euler circuit. So we go across the top edges, down, back to the middle, cover those edges in that inner loop, back toward the left, and back up to the top, right? So in an Euler circuit, we're covering every edge of a graph exactly once. And we saw that it's easy to tell whether or not a graph has an Euler circuit, because an Euler circuit exists if and only if the following statements are true. 1, the graph is connected, and 2, every vertex in the graph is even valent. Okay, so those are our Euler circuits. What about a Hamiltonian circuit? So in a Hamiltonian circuit, rather than visiting the edges of our graph, we're visiting vertices. So in some graph theory problems, it's only necessary to visit specific locations using the travel routes or streets available. And so a tour that starts at a vertex and visits each vertex once and only once, and then returns to where it started, is called a Hamiltonian circuit. Our goal is often to find an efficient route along distinct edges of a graph that visits each vertex only once in a simple circuit. So what are some real-world applications of these Hamiltonian circuits where we're visiting vertices? Well, one example would be a salesman who needs to visit particular cities, or someone who is inspecting traffic signals, any sort of delivery person, UPS, pizza, dry cleaning, florist, etc., or a pharmaceutical rep visiting doctors. So what about you? Have you ever had a job that required you to visit vertices? Notice in each of these, we're not needing to cover every single edge. in the case of our delivery person, that pizza delivery person doesn't need to travel along every possible road, right? They just need to hit the houses they need to visit and then go back to the location where they started. So with Hamiltonian circuits, the key is that we're visiting every vertex exactly once and then ending where we started. Now, with our Hamiltonian circuits, unfortunately, there's no simple way to tell if a graph has a Hamiltonian circuit like we could with our Euler circuits. But keep in mind, we do not need to traverse each edge, we're just hitting each vertex. Hamiltonian circuits are named after William Rowan Hamilton, an Irish mathematician, although the concept was discovered by British minister Thomas Kirkman. So these Hamiltonian circuits are a tour that start and end at the same vertex. That's our definition of being a circuit. And they visit each vertex once. Note that vertices cannot be reused or revisited. Now our circuits can start at any location, and we often use wiggly edges to show the circuit. Here you see in graph A, a Hamiltonian circuit starting at the vertex A. So if we start at A, our circuit goes from vertex A to B to D, G, I, H, F, E, C, and then back to A. So we have visited each vertex of the graph exactly once and started and stopped at the same vertex. Here is a different Hamiltonian circuit on the same graph that we see here in B. If we want to start this one at C, at vertex C, we could write this circuit as going from C to D to B to I to G to F to E to H to A, and then back to C where we started. All right, here's some examples. You may want to pause the video and play with these and see if you can find a Hamiltonian circuit for each one of these graphs. Okay, so I've taken these graphs and moved them into paint so that I can draw on them. So starting in graph A, suppose we want to start at the vertex x1. And remember, we want to hit every vertex exactly once. So I'm hitting every vertex exactly once, and now I'm going to go back to where I started. So there's an example of a Hamiltonian circuit in graph A. Now graph B may be a little bit trickier, so let's see. So if we just dive in, maybe we say, okay, let's try to work our way along the outside first, and then bring our way inside, and now, we're stuck, right? There's no way going along the route that we have started with here that I can hit every single vertex and end back where I started. So we say, okay, that one didn't work. So I'm going to undo all of that, and let's try again. Okay, so here's another attempt. So this time, let's go down and work our way back inside, and I'll kind of wiggle my way along the inside here, and now kind of work my way back and forth between the outside and the inside, and it looks like that one is going to work. So that particular example gave us a Hamiltonian circuit on graph B. What do you think about for graph C? So here's one option. If I go down, back, around, and then I'm going to work my way to the outside, back in, and up. Okay, so there's another, there's a Hamiltonian circuit in that example. Okay, here are two others for you to practice, and I do recommend that you pause the video and play with these and see what you come up with, and then I will give you an answer. Okay, so here's an answer in graph A. We can start here and work our way around, and now kind of go in one layer and then around. So just kind of working our way inside, 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 back to the middle, and then I had to leave myself a way to get back out, right? So there is an Hamiltonian circuit for graph A. Sort of similarly for graph B, I'm going to kind of do something similar where I'm going to kind of weave my way in and out. Got to be a little bit careful. Make sure I'm hitting every single vertex exactly once, and then that I have a way to get back home to where I started. Great, so there's a Hamiltonian circuit in graph B. Okay, so we've seen some graphs that do have Hamiltonian circuits. Here is an example of a graph that does not, so that you can see that not every graph has a Hamiltonian circuit. So here's one. This is an example of what's called a KMN graph, which has M vertices on one side, N vertices on the other side, and each of the M vertices on the left are connected to the N vertices on the right. That's how these graphs are created. All right, so if we try to find a Hamiltonian circuit on a graph like this, so if I start up here at this vertex in the top, and I have to work my way to the other side, and then back to the left, back to the right, back to the left, but now I'm stuck, right? I have not visited every vertex yet, and there's absolutely no way for me to get back home to where I started without reusing a vertex. So no Hamiltonian circuit exists for this graph. You will always need to pass through a vertex more than once in order to be able to return home. And the key to the problem with this MN graph is that M is greater than N. So anytime we create a KMN graph where M is greater than N, then that will be an example of a graph which has no Hamiltonian circuit. Okay, so to wrap up this introductory video, I want to do a quick comparison of these new Hamiltonian circuits with our old Euler circuits. So the Hamiltonian circuits, remember, are a tour, often showed by wiggly edges, that start at a vertex of a graph that visits each vertex once and only once, and then returns to where it started. An Euler circuit, on the other hand, is a circuit that traverses each edge of a graph exactly once and starts and stops at the same point. So for our similarities between the two, they both forbid reuse, right? And the Hamiltonians were not allowed to reuse vertices, and an Euler circuit were not allowed to reuse edges. Another similarity is that they are both circuits, so they both start and stop at the same vertex. But the difference is that a Hamiltonian is a circuit of vertices, whereas Euler is a circuit of edges. Now the Euler graphs are easy to spot. We just have to check for connectedness and even valence. But the Hamiltonian circuits are not as easy to determine upon inspection. So we saw there's at least one family of graphs that we know do not have Hamiltonian circuits, those KMN graphs, but there are lots of other graphs that are not KMN, but that also do not have Hamiltonian circuits. So it's hard to determine whether or not a graph has a Hamiltonian circuit or not, which is different from our Euler circuits. Okay, so that's all for our introduction into Hamiltonian circuits. In our next video, we're going to start to study something called a minimum cost Hamiltonian circuit, and I'll see you there. Thanks, guys.